Okay, so our first speaker in this session is Mathilde, and she will talk about COVID-19 in Switzerland. Over to you, Mathilde.
Okay.
And I'll raise my hand when you need to kind of contest.
Okay. So you hear me all right? Yeah, okay. I'll try to look at both screens at the same time. All right, so I'm going to present some work that we did in Zurich with Leo and Maria and Felix last spring on incorporating time-dependent weights in the endemic-epidemic framework, in particular in this pandemic context, to model the effect of border closures. So I'll recap some of the features or important features of infectious disease data and why we need the appropriate models to analyze them. So an important feature of the infectious disease outbreak data is that they're highly dependent, right? And so we're using highly dependent in the sense that every case is caused by another case, right? So you have that dependency structure in the data. And this, we require transmission models to capture that dependency in the data. So the endemic epidemic framework, as we've said multiple times, is a two-component model. We have on one side the epidemic incidence that captures the incidence driven by previous case counts in all regions. So that's an autoregressive. Everything okay?
I don't know where it is. Where is it? Okay, keep going. It's not about.
Oh, okay, okay. That's the autoregressive process. And then we have the endemic incidence that captures pretty much the rest, right? The incidence that can't be explained by the epidemic component, and that's due to exogenous factors. So if we zoom in on the epidemic part, right, we've talked a lot about the weights that drive this autoregressive process. The autoregressive process is driven by contributions in cases from other regions. So that's the spatial part of the transmission, which is determined by this weight matrix W. And contributions in cases on previous days. So that's the temporal aspect of the process. And that's determined by the serial interval UL. So now I'm going to go a bit into how we're going to define these autoregressive spatial weights. The spatial contribution from one region to another region is determined by their spatial relationship, right? The closer two regions are together, the more they're going to exchange cases, and the further they're apart, the less they're going to influence each other's incidence counts. And we can summarize that spatial relationship by the spatial relations matrix W. That can look something like this, right? We have regions organized in both dimensions of the matrix. They're ordered arbitrarily. And the closer they're together, the stronger the dependency. Here we have the strongest dependencies in lighter colors and the weaker dependencies in darker colors. Now the question is how we want to quantify that strength of spatial connectivity. So there's two ways that we can do this, and we've addressed both methods in this morning's sessions. The first one is model driven. So that's with the power law, which, as was explained this morning, is just a way of quantifying this decay of connectivity as spatial relationships, as the spatial distance increases. But then we can also have a data-driven approach, right? We can introduce real-world data, such as travel or commuting data, to determine how strongly two regions are connected. What we propose in this work is a combination of all of this. We started out with the static power law. And the power law is very nice to describe the spatial relationships as they were pre-pandemic, right? They don't really change over time. The strength is of that spatial connectivity is pretty much established. But arguably, this is not really reasonable in a pandemic context when borders closed and just traffic in between regions, mobility was reduced. And so we proposed two adjustments, two data-driven adjustments to that model-driven power law approach. So first, we've included an adjustment for accounting for the changes in mobility intensity. And so we've used smartphone data that has tracked the amount of movement that people have done during the pandemic compared to how much they moved before the pandemic. And this is daily data. So for each day, we have the change in mobility compared to a pre-pandemic context. And then we have changes in travel restrictions. So there we used indicators of border closures as provided by the International Organization of Migration. And these are just very simple 1-0 indicators for closure or no closure of border. And this is what weight matrices can look like after these three adjustments. So you see the more you move over time here, the darker the spatial connectivity gets, indicating this change in mobility and changes in cross-border travel. So this is, if you move down, this is over time. And if you move left to right, you have the power law adjustment, which is not time dependent, and then the Facebook adjustment and the IOM adjustment. Okay, and here you can very clearly see pretty dark blocks here, indicating really the border closure between Swiss and Italian regions. So this, as you see, is now a time-dependent matrix of spatial weights, and this allows for the simulation of different border closure scenarios. So a tiny bit of context on border closures as a pandemic countermeasure. Of course, you're probably very familiar with it by now, but this is a countermeasure that's been used in different, used and studied in different epidemic and pandemic contexts. And in the context of COVID-19, by the 20th of April of 2020, then some form of implementation of travel restrictions has occurred in every country of the world. The effectiveness of border closures remained fairly unclear, which is why the WHO first advised against border closures. And so to study this a bit further in the Swiss context, these are the regions that we take into consideration. We have all of the Swiss regions, and then the 4 bordering Italian regions here. And we consider the time frame from the first case that occurred in Switzerland until the summer. So we have a time frame of approximately 4 to 5 months. So the way that we proceeded in our study was we started out by fitting an endemic-epidemic model to this region stratified time series of COVID-19 cases. Then using that model, we did some retrospective simulations of counterfactual scenarios of border closures. One scenario that we studied was just a closure of borders as they were implemented in reality. This is our baseline scenario that we're going to compare everything to. Then we have the scenario where we just don't close any border for the whole study period. This is counterfactual scenario A. And then the closure of the Swiss-Italian border 2 weeks earlier. At that time, there was a lot of discussion whether the border just had been closed too late to have any effect. So this is another scenario that we are studying. So before we go into some results and some more detail about our model, it's important to take some of our assumptions into consideration, right? Because they modeling assumptions influence the results that you see a lot. So the first assumption that we made is that when we adjust for a border closure, that adjustment is homogeneous throughout the regions of a country. So what I mean is, for example, if we close the Swiss-Italian border, the contribution of this Italian region will be changed by the same factor for all of the Swiss regions. Okay. And the second assumption that we made is that the Facebook adjustment that we do on top of the border closure adjustment pretty much accounts for all of the other social distancing measures that had some impact on mobility beyond border closures. The model covariates that we considered in the endemic and epidemic log linear predictors were weekend and public holiday indicators, because just healthcare seeking activities vary on the weekends. We have a country indicator, border regions indicators, testing rates, temperature, the level of urbanization, so how dense a region is. We have a linear time trend and a nonlinear seasonal time trend, and a gravity model, which just captures the phenomenon that we observe that bigger, denser populated regions attract more cases usually. So this is what the model looks like after we fitted it. We have in yellow the share of endemic transmission, and in blue the share of epidemic transmission. And what's really interesting to see here beyond just model fit is really the share of endemic to epidemic spread, which is really an interesting characteristic of the EE framework. As you see, the highest share of endemic spread happens in the Italian regions and in CH01 and 07, which are the two key border regions. And this makes a lot of sense given the history of the transmission that happened, right? The first cases happened in Italy and then transferred over to Switzerland via these two regions. Then based on this model, we did these three predictions, as I've explained. We have the baseline scenario in pink, scenario A, so with no border closures in blue, and scenario B, so with the border closures 2 weeks earlier in yellow. So we really see that in Switzerland, border closures, or in fact, having no border closures would have had a drastic effect on case counts, especially as you see in the first wave. So between March and June, it would have on some days more than doubled the incident cases. And another thing that you see is that closing the borders 2 weeks earlier really had very little effect compared to the baseline scenario, which all in all just shows the support for the baseline scenario and for border closures as they were implemented. So to finish off with some discussion, I'll go through some strength and limitation of this project. Some strengths first, of course, main strength here is the use of the very flexible endemic-epidemic framework that does a very good job at capturing the spatial dependencies in incidents. Then I find this quite interesting that we use all of these external sources of data to kind of strengthen the model-driven approach and to complement it in a nice way for this pandemic scenario. Then this novel approach of having these complex time-varying spatial relationships beyond these static weights is a nice addition to the EE framework. And then we've thought a lot about how to quantify uncertainty here. So we've included the uncertainty, the internal uncertainty of the model parameters in our prediction, but also some external uncertainty that came about from the power law formulation in that parameter. And of course, this work can help support decision-making about pandemic countermeasures in general in the future. And then to close off, some things that we might want to do differently or in further work. First of all, we assumed in all scenarios that the only changing effect would be border closures, without considering that border closures could in turn have some effect on other countermeasures. So we didn't really include that. And then in all the different scenarios, we use the same model parameters, which is quite related to that other limitation. So, sorry. Thank you. Of course, this was very short for a lot of work. So if you want to have a more in-depth, we have a public Git repository that summarizes all the work that we did. All right.
Thank you very much. Right, so in the interest of time, we'll go straight to the next speaker. But if you have further questions to Mathilde, please put them in the chat. She'll be able to answer them there.
Need to.
I think it's best if you don't go full screen, because that's what broke it earlier. So
Okay.
if you just do it from this,
Okay.
and you can click on the left, you can click on the next slide if that's okay. Great.
Good afternoon, everybody. So first of all, thank you very much for giving me this opportunity to be in London for the first time. And my name is Trang. I am a first-year PhD student at Hustle University, and today I would like to present our work with the spatial temporal modeling of an outbreak of measles in southern Vietnam. A part of this presentation is from my master thesis. So for me, it's a very first study about infectious disease modeling in general, and in particular, the spatial temporal modeling. So in this presentation, I will start by describing the study setting, as I think many of you have not very much familiar with the southern region of Vietnam. And I will then introduce to the measles data together with the two applications of the data for the hh4 models. One is a spatial temporal model, and the other is an age-stratified models. And by the end of my presentation, I will discuss about the study limitation and some further considerations. So first of all, about the study settings. So we focus on the southern region of Vietnam, which is the purple part in the picture of your right-hand side here. The southern Vietnam regions comprise 2 cities and 18 provinces. So from this moment, I will use the word province for the convenience of the presentations. So according to the census data in 2019, the total population is estimated is 36.4 million of people in an area of 74,000 square kilometers. With a closer look to the population in each province, it is interesting to know that Ho Chi Minh City is the most populous city in the region, with the approximate 9 million of people, while the population in other provinces range from 1 to less than 3 million people. And the fraction of children under 15 accounted for 21.6%, and those under 5 years old accounted for 6.7% of total. So now we move to the data source. In Vietnam, measles are required to be reported case by case to the National Electronic Communicable Disease Surveillance System, and within 24 hours after diagnosis. So in October 2020, we retrieved a line list of more than 26,000 cases reported between 2018 to the first 6 months of 2020. And the advantages of this data set is that it's not only provide the demographic detail of the case patient, but also the time course of disease, including the date of illness onset. So I hope this figure here can give you an overview of the outbreak situations. So the daily numbers of infections started to increase from August 2018 with 2 peaks in March 2019 and in January 2020. The children under 5 years old was the most affected groups with 61.4% of the case were our children. And interesting to know that in 2019, 19 over 20 provinces had an incident per 100,000 populations greater than the national target of 7.5 cases per 100,000 populations. And so to illustrate the data, the disease spread in a spatial temporal model, we fitted an endemic-epidemic multivariate time series model under the assumption of homogeneous mixings. So here we use the daily counts of measles infection by provinces in 1.5 years. So our final model was the model we incorporated the log population, the log province-specific proportion of susceptible populations as covariate here in the endemic and autoregressive components. And you see here the VR is the vaccination coverage of the first dose of measles containing vaccines in 2019. And we also include the spatial interactions using the power law ways and also the random effects in the 3 components of the models. And here in the plot of fitted model here, we see that the model captured really well the observed data, and the epidemic behavior was dominant. It was clearly illustrated when 95% of the risk was attributable to the 2 epidemic components. And when we stratify by province, the transmission between provinces was prevalent in most areas, whereas the local transmission was dominant in only 4 provinces, which are marked in the pink star right here. In the next slide, I'm going to spread a little bit more detail a transmission pattern of the measles outbreak. So when we look at the when we check with the coefficient of the model, we found that the incidence of measles was associated with the heterogeneity in vaccination coverage, which is ranged from 18 to 98% in each provinces, and predominantly exhibited an adjacency-based spatial temporal model. And for measles, as you already know, the transmission can only be sustained when the susceptible population has sustained had a suspicion size. So in our setting, the increased susceptibility can be due to the discrepancy in immunization protection and low vaccination coverage in different age groups, as well as the social economic inequalities, such as the education of parents, for example. And therefore, this is critical to track the uptakes of the measles vaccine in the populations. And when we look at the spatial interaction here, the decay parameter here is quite high. So we see that the transmission from nearby province would attribute the stronger link to the size of the outbreak. And we also found a substantial spatial difference of the incident level in the autoregressive component and also the spatial temporal component. So the possible explanation here is maybe because of the underreporting due to the diagnosis practice. For example, they diagnosed at typhus fever which is the ICD-10 code is A75. However, for the measles, the ICD code would be B05. It's different code in ICD-10. Maybe for another possible explanation is the older case, maybe a lack of medical attention, the community case from that we cannot detect from the surveillance system, and also the imported case from outside of our study settings. So in order to have a better understanding about the transmission dynamic with the same data set, we did another study using the model with the age-stratified spatial temporal analysis. So this time we, because of the limited data of the vaccination, so we did not include the vaccination coverage data in as covariate in the model. So this model we use here is somehow is a classic regression model. And the figures show here the fitted component from our model. And it is apparent that the measles is a childhood disease. And in the youngest age group, uninfected individuals is more likely transmitted to unsusceptible person within their age group. However, is a high proportion of between groups transmission in older groups, suggests that susceptible adults maybe increase exposure to measles and acquire infection from their children, possibly via childcare at home. And about the spatial interaction between geographical units, so we found that it follows an age-dependent distant decay. So we observed that in groups in the youngest age group, the power law put more weight on the first and on the local and the first order neighbor transmission, while in the older age group there was a faster distant decay of transmission from the nearest neighbor. So it implies that the infection in older age group was more likely to happen within their resident home, their home resident, whereas case in the young children possibly depend on the past case from the same or in the neighboring province. And that's all our work about the measles situation in Vietnam. But however, we are aware that there is some several limitations in our studies. So, for example, in the spatial temporal analysis, we use only the first dose of measles containing vaccine coverage data as proxies to infer susceptibility levels, and we did not make any assumption on the correlated random effects, which might be satisfactory to account for the unobserved heterogeneities. And for the age stratified spatial temporal model, we rely on the number of contacts between age group retrieved from a survey in northern Vietnam in 2007. So the contact patterns is in the southern region might be significantly different after a decade. And in both models, we have not yet investigated case at higher order lags, as also the performed simulations, as well as taking a closer look to the effects of underreporting. And we also think that we use the approach from the authors to fit the data, rather than adapting them to understand the spatial temporal dynamic. However, for a newbie like me, and for those people who have not much statistical skills, and the modeling frameworks and the surveillance package can really be handy and easy applicable to the real-life setting like this. And that's bring me the end of my presentation. So thank you very much. Many questions. I'm very much happy to answer. Thank you.
Thank you very much. Yeah, because since we're running slightly behind due to our technical inaptitude, we'll do questions in the chat, if that's okay.
Yeah.
And we'll go straight on to the next speaker. Okay. One of them. This one maybe, no. Okay, great. So slightly shorter interlude this time as we are getting better at working out the setup. So next up is Claudio Fontella from Lancaster. Over to you, Claudio.
Thanks. Hello, everyone. Thank you for the invitation. My name is Claudio Frontera. I'm a lecturer in biostatistics at Lancaster University in the CHICAS research group. And today I'm going to talk about some spatial temporal modeling of COVID-19 in England. This is actually some work that I've done almost 2 years ago. Indeed, the data that I'm going to show refer to the first year of the pandemic, although we kept applying for a while this modeling setting, keep updating our prediction and releasing them online openly. So the motivation for this work was we wanted to integrate all the data that were publicly available on COVID-19 and some auxiliary information to build a real-time surveillance system. So something that we can update on a daily basis to track how the pandemic was evolving over time in England, and also with a focus on providing short-term forecasts and do a little bit of anomaly detection, trying to raise some alarm when we saw that in some part of the country something strange was going on. And after a little bit of search, when I look at the endemic-epidemic framework, I thought that that was a very nice approach because it's very flexible. And also, as you saw, you can fit those models very quickly. So it allows for essentially near real-time surveillance. So this is the first year of data from the COVID-19 pandemic in England. We start to see the first cases in March 2020, mid-March 2020, and by the end of the year, we really had the first two kind of endemic waves. And by a simple look at the time trend, we can see a couple of features that will have to reflect in the way we build our model. The first is this drop in the number of reported cases that you see every week. So you have this artificial weekend effect. It's not, of course, a feature of the way the disease spread. It's just because these are reported cases, not the true number of infected people. So there are less number of tests, less testing is conducted over the weekend. So we'll take that into account in the model. And as if you focus on the last days of reported data over the year, then always the last 4 to 5 days, there is a delay in reporting. So those last days of reported cases are not reliable, so we simply remove them before starting analysis. And the way we have kept updating this model, we don't assume that over a very long time of period, the property of the model and the parameter of the model are stationary. So essentially what we do at every time point, we keep we exclude the last 4 to 5 days, and we take only the last 60 days worth of data. We feed the model on those 60 days, and then we predict 1 week ahead, and we compare those predictions with what observed to see if what we observe is expected or is not. We use both pillar 1 and pillar 2 data. The pillar 1 data in green are the ones that essentially were provided at the very beginning of the pandemic, and those are people with clinical needs that are being tested in NHS and PhD labs. While around April, May 2020, then the government also started other testing programs to test more wider the population. Those will be the pillar 2 data. So for example, the self-testing kit that we receive when you do a test at home and then you provide the results, that will go to the pillar 2 data. And we analyze both of them simultaneously. And of course, as you can expect, there is a lot of spatial variation in the incidence of the disease across the country. The level at which we conducted the analysis is the lower tier authority level, LTLA, and we have 315 geographical units for all England. So our kind of full data set is composed by every time that we fit the model, we have 60 data points per 315 geographical units. Our, let's say, first attempt at modeling this data was with, let's say, the vanilla version of the endemic-epidemic framework. So we model the current number of cases just conditionally on the last observation. And we decompose, as usual, the mean of that negative binomial distribution for the reported cases in 3 components. So the intrinsic, or what we have called so far the endemic part of the model, plus the epidemic model that looks at within transmission, and the epidemic part of the model that looks at transmission between different geographical regions over time. And then we have these 2 parameters, lambda and phi, that control how much the past number of cases, both within a specific geographical unit and coming from other geographical units, will impact the future time trend. And another essential part of this model we saw is this set of spatial weights, and I will talk briefly about how we parameterize that. This model can actually be derived in a couple of different ways. So originally, Leonard Held derived this from a branching process, but later, a few years ago, John Wakefield in a paper showed that actually you can obtain this vanilla version of the endemic-epidemic framework, starting from an SIR model with a serial interval equal to 1 time period. So what does it mean is that with this model, we're implicitly making the assumption that the infectiousness lasts for exactly 1 day. And from a lot of, there is a lot of evidence that, of course, that is not the case for COVID-19. So you have 2 possible options in this scenario. Either you aggregate the data, okay, maybe to weekly, to whatever you think is a more realistic infectiousness period, or you can use a nice solution that Johannes and Leonard came up with in this paper in 2020, where you condition not only on the past time point, but on a series of D lags, and you weight those lags using some distributional parameter we infer from the data, and the distribution of that weights then will resemble the serial interval. So that's what we this is the type of model that we fit for the COVID-19 data in England. The way that we tried a couple of parameterization for the weights, both geometric and shift Poisson. The main difference I would say between these weights is that the geometric weights, these are formulated in such a way that the first weight has to be the largest, okay? So they cannot increase and then decrease. They will either be kind of steady, or they will simply decrease with increasing number of lags. While the shifted Poisson type of parameterization for the weights of the lags is more flexible because we can have also weights that increase and then decrease. So this is how we parameterize the weights for the lagged observation. When it comes to coupling together the different geographical areas, as you saw, you can either use something like a power law, or if you have some real data available, probably it's a good idea to use them, because we try to want to resemble as much close as possible the way in which people interact between these different spatial units. So what we did was to take some commuting volume data from the 2011 census that give an idea of how much journeys are made from residence to workplace between each of these spatial units. Now, the issue with this is that, so you come up with this square metric whose dimension is the same of the spatial units in your model. The issue, of course, is this gives us a picture of what was the behavior of people moving around before the pandemic. So what we did to take into account the fact that people were moving less and changing behavior in response to lockdowns and other measures was to use some data on traffic flow. Although this is a country level, so we're kind of making the implicit assumption that I mean, the change in behavior of movement is kind of homogeneous around the country. So we use this traffic flow data to modulate the commuting volume after lockdown. So you have the reference value before lockdown, that will be 100, and then you see this is the effect of the first lockdown when people start to move less and less. So we take this into account to scale that weighting matrix of commuting and have a more realistic representation of how much the spatial units are connected with each other. Then just a little bit more about how we formulated the model. This is how we specified the 3 different model components. So for the endemic part of the model, we use population as an offset. If data were available also on the age distribution of the cases, actually you could use some expected number per age that will probably give you a much better standardization. Then we have a linear time trend and a binary indicator for the weekend days, and that is to correct for that artificial weekend effect that I showed at the beginning. For the within region part of the model, again, we use that, we introduce a population offset and then some an independent set of random effects that are specified at the spatial unit level. So we allow the, let's say this within transmission to vary by spatial region, because we expect that to be very different from one LTLA to the other. And then for the between part of the model, we got to offset there both the population and our data on the traffic flow to in such a way. So if we put this as an offset, then it will modulate and scale down the weight matrix in a proper way. And then one of the main outcomes we were interested in was to do short-term predictions, to just predict for days ahead. This is fairly straightforward with this model, because one step ahead predictions are all negative binomials. So to do k step ahead prediction, you can just use Monte Carlo simulation and sample from the predicted distribution at any time point. And the way in which we conducted anomaly detection was simply to look at the probability that the total number of observed cases in the last week that was out of sample, that was not used to fit the model. So if that was greater or not, that what the model predicts. If the probability of that event was greater than 90%, then we would raise a red flag. I just want to highlight some results on the on how we choose how many lags to include the model. We simply fitted a lot of different models with the 2 different parameterization and with an increasing number of lags, and we look at the improvement in the AIC as compared to a model without the lags, and we saw that it kind of stabilized around a lag equal to 7. So then we fitted 2 models with those 2 lags, and also according to this, there is a smaller advantage to use geometric as compared to Poisson weights. But then when we look at the estimated weights, Poisson weights made more sense from an infectious disease point of view, because this distribution, the blue one, represents much better what we saw in other piece of research that look at the serial interval distribution for COVID-19. And I'll go straight now to, yes, I think I need your help.
Yeah. Yes, we reshare. I just do this. Okay.
Okay, thank you. So to make to provide the results on this model, we implemented everything in such a way that every day we get the data inputs, we refit the model on the last 60 days, taking out the last week worth of data. And then for every region, let's take something in London, Greenwich, then essentially the blue part, this will be the points used to fit the model. And these red cross are the all that observation. And then we compare the prediction from our model with what we observed. So we look at the total for that week. And if there is a high probability that the total number of cases reported in that week is greater than what the model predicts, then we raise a flag, raise a warning. And we say that there is probably some anomaly going on, probably the trend is changing. So that is how we use this, this model for a while. And yeah, that was all for me. Very happy to take any question if we have some. Thank you very much.
Very much, Claudia. Thank you. Great. So again, we'll just do questions in the chat, please, and in the interest of time, and so we still get our coffee, we will straight on to the lesser technical challenge of having an online talk from Johannes. Over to you, Johannes.
Thanks a lot. So I'll share my screen. Can you see those slides in full screen now?
Yes.
Okay, perfect. So yeah, this is actually less of an application than a more detailed theoretical look or statistical look at the impact of an aspect we sometimes neglect in these analyses, which is underreporting of disease surveillance counts. Okay, I have a little motivating example, which is rotavirus in Berlin. You may remember that from this morning. So it's a gastrointestinal disease affecting mainly young children. It's vaccine preventable actually, but we're looking at pre-vaccination data. Mean serial interval is at roughly 5 days. And this disease is known to be subject to strong underreporting. So that's a study from a couple of years ago, which states that in Western Germany, and we count Berlin to Western Germany in this case, only 1 in, let's say, 20 cases is really reported of that disease. And yeah, what I've been looking into is how this phenomenon of underreporting affects things when we work with this endemic-epidemic modeling framework. In particular, when we use it to estimate local reproductive numbers, which is something I think CC Bauer will also talk about in her talk. Okay, I'll jump right into the model definition. You're probably familiar with that by now. So this will all be in the univariate case because yeah, I had to keep things simple to get the theory to work. But anyway, as always, we have this decomposition into a constant, this endemic term, and then an autoregression on the past value, this phi times x t minus 1, and then the model has this simple Markov structure. And as we've seen a couple of times today, oh, okay, yeah, let me give you some more intuition, sorry. So this is cases that come from somewhere else than last week in the same region, and these are cases that come from what happened one time step ago in the same region. And then if you assume that the serial interval is exactly 1 time unit, then this phi parameter can be interpreted as a local effective reproductive number. And this system has kind of a stationary state if phi is smaller than 1, and on average we'll have nu over 1 minus phi new cases per week. Okay, actually I'll be working with a slightly generalized version of this model. As in previous talks, I'm adding a kind of higher order dependencies, but I'm doing that slightly differently than before. I'm adding a lagged version of the conditional expectation to this, which is what is done in InGarch models. Maybe some of you know this, but that's just a different way of writing geometric lags, actually. So you can rewrite this formulation as such a model with geometric lags, and the serial interval distribution would then have a mean of 1 over 1 minus kappa, and the effective reproductive number is just phi over 1 minus kappa. So that's just a different way of writing things down, and it makes it easier to get the theory done. Okay, and this is kind of the new bit here, we assume that we don't really observe this X process here, but that there's an additional reporting process, so that's binomial here, and we have this X tilde process, which is what we actually observe. So this is latent, this is observed and can feed into the model fitting. Okay, and now that's quite a bit of theory in that paper, but I'll try to break it down without formulas. So as long as phi plus kappa is smaller than 1, so it's kind of subcritical, this model has certain stationary properties in terms of means, variances, autocorrelation functions, and all that. And you can derive that both for process with and without underreporting. And it turns out that those properties don't qualitatively change, let's say, if you add a reporting process to your model. And it can even be shown that different combinations of those 5 parameters that the model then has, so nu, phi, kappa, psi, and pi, can lead to the same second order properties of that model. So different parameterizations of the model kind of imply the same observable processes, almost, let's say. So putting it this way, so for each model of this more complicated structure, there's actually a simpler model of this form that behaves almost exactly the same way. So what does that mean in practice? So that means that the model is over-parameterized, that you can't identify it. And in particular, you cannot estimate the reporting probability just from the observed data that you have. That's also something you observe in other models. So typically, you can't estimate that just from the data that you have from your time series. On the other hand, all the theory that I derived implies, allows us to quantify the expected biases that we would get if we fit such a model to data without accounting for underreporting if really they are underreported. And one can show that one will underestimate the effective reproductive numbers, one will overestimate the share of imported cases, and one will overestimate the mean of the serial interval distribution, which I think is interesting from an applied perspective. But what's nice is that all this kind of theory on almost equivalent models that we have in this paper also allows us to put in place a very simple inference scheme. So and I'll try to sketch that here. So we'd like to do likelihood inference, but it's difficult to evaluate the likelihood of such 2-level models. But as we have all this theory of approximating more complex models by simpler models from the same class, we can also get good approximations of their likelihoods. And then essentially we just use that in the likelihood optimization, given a reporting probability from the literature that we need, because otherwise the model is not identifiable. And then we can fit this very quickly. So you don't need any MCMC or those kind of things. And this also nicely generalizes to time varying parameters or even temporarily aggregated observations. So you can define a model on a finer time scale than what you observe. We have a few simulation studies in there. I think in the interest of time, I'll skip through that fairly quickly. Essentially, they show that the method that we came up with avoids biases in the parameter estimates, while ignoring the problem of underreporting will lead to biases, which we can actually predict and quantify very accurately. Okay, and to circle back to our applied questions, a little model for rotavirus. So here I used a model which has seasonality in those 2 components and then has underreporting with given reporting probability, which will vary between 0 and 100 and see how results change. And then we also have this temporal aggregation step in there, which I kind of smoothed over before, but yeah, we can also do that using a methodology that we have. And now we'll just fit that model using different values for the reporting probability between 2% and 1. And then we get kind of parameter estimates for the different parameters depending on the reporting probability that we put into the estimation procedure. And what's probably the most interesting panel of this plot is this one here, which shows the effective reproductive number over the course of a season. So 104 half weeks we have here, depending on the reporting probability that we assumed. And we can see that if we assume complete reporting, then we get much lower estimates. And if we assume a low reporting probability, as the literature indicates, we get much higher estimate. So summarizing this, so if we assume the value from the literature, we get a mean serial interval of 6 days, and the local effective reproductive number is between 0.72 and 1.02, which then, together with some imports of cases, leads to the stable seasonal pattern. And under this model, we would estimate that 1 in 10 cases is imported from outside Berlin. And if we assume that reporting is complete, which is obviously wrong, but we do this for comparison, we get a longer estimated serial interval and a lower reproductive number and a larger share of cases that are imported. So I guess the conclusion is that results you get from such a model can depend quite a bit on what you assume in terms of reporting. And importantly, you'll tend to strongly underestimate reproduction numbers based on such a model if you ignore underreporting. It's kind of an attenuation phenomenon. And yeah, just as a note of caution, one could argue that even these reproductive numbers are kind of low, and that 1 case in 10, which is imported from outside of Berlin, is a lot. It's kind of coherent with commuter stream data, but given that it's more prevalent among children, it's maybe not such a credible argument to make. Okay, so yeah, that's what I had to share. Thanks a lot for your attention, and yeah, looking forward to the other talks.
Johannes, you just got a round of applause here, which you didn't hear, sorry. But it was enthusiastic. Great, thank you very much. And thanks again to all the speakers in the session. So please continue to use the chat if you have any further questions to Johannes or any of the other speakers. We will break now for what's left is 23 minutes. I'm just going to stop the recording as well if I can.